problem 5 says that an unbalanced chemical equation, and it gives us the equation. If you begin with 400 milliliters of N2H4, and it gives us the density value, and 625 milliliters N2O4 with a density value, how many liters of water vapor will theoretically be produced? So this is a limiting reactant problem. It gives us two different given values, and we need to figure out how much product is produced by each. But first we do need a balanced equation, and while it gives us the equation here, it is unbalanced. So we'll go ahead and take a look at that first. So right away, this is going to be complicated to balance because I have nitrogen in two places on my reactant side. And I think that's actually it. So maybe we'll just leave nitrogen until the end. We'll fix hydrogen and oxygen first. So I see there are 4 hydrogens and only 2 on the product side. So I'm going to double the number of water molecules. Now I have 2 oxygens, and actually I have 4 on my reactant side, so I'm actually going to have to change that 2 that I just wrote down to a 4 to fix the oxygen imbalance. So now I've balanced oxygen, so I'm going to have to take another look at hydrogen. 2 times 4 gives me 8 hydrogens on my product side, so I also need 8 on my reactant side. So 2 times 4 fixes hydrogen, and now that we've fixed both oxygen and hydrogen, we'll take a look at the nitrogen. So coming from the N2H4, we have 4 nitrogens, and then coming from the N2O4, we have 2 nitrogens, so that is a total of 6. So I also need 6 on my product side, so I'll put a 3 in front of N2, and that should balance everything out nicely. And you don't have to, but I like to fill in a 1 into that leftover blank spot. And then I'll erase these random numbers just so we're not getting confused. And now we can do our limiting reactant problem. So we will, of course, start with both given values. We'll start with 400 milliliters of N2H4 and 625 milliliters of N2O4. So let's see, 400 milliliters of N2H4. And now, since we have milliliters is not on our stoichiometry flowcharts. We are going to first have to use the density that's provided to get that into grams. And so we will just convert milliliters of N2H4 to grams of N2H4. And then our density value says that the density is actually just 1 gram per milliliter. So 1 to 1 gram per 1 milliliter. Then we will be able to go from grams of N2H4 to moles of N2H4. And then finally we will go from moles of N2H4 to moles of our desired product, and it is we have 2 products here, but it's asking us how many liters of water vapor. So I'm going to go ahead and convert these to moles of water, moles of H2O. To determine the limiting reactant, it doesn't really matter which product we convert to, as long as we do the same. We convert to the same thing for both reactants, but since it's asking us to find the theoretical yield and it's not just asking to identify the limiting reactant, we want to make sure we find the theoretical yield of the desired product, and it says liters of water vapor specifically. So that's why I'm going straight to H2O. Now we'll do the same thing for our N2O4, starting out with 625 milliliters of N2O4. Notice these are very similar looking reactants. We have N2H4 and N2O4, so it is critical that you write correct formulas. First we'll take our milliliters of N2O4 into grams of N2O4. And to do that, we'll use our density value that's provided, which is that 1.44 grams per milliliter. 1.44 grams per 1 milliliter. Then we can take our grams of N2O4 to moles of the same substance, N2O4. And then we'll do our mole-to-mole ratio. So moles of N2O4 to moles of our new substance, which since we converted to moles of water in the first one, we definitely need to convert to moles of water in the second one so we can compare the amounts produced and figure out which reactant will be the limiting reactant. So for our mole-to-mole ratios, we know that it's not necessarily a 1 next to mole. We are going to look back at our balanced chemical equation. So for H2O has a coefficient of 4, and so on top of both my mole ratios I will put 4 moles of H2O. And then N2H4 has a coefficient of 2, so that's what we put in front of N2H4, moles of N2H4. And then last but not least, N2O4 has a coefficient of 1, so this is a 4-to-1 mole ratio. Now we just need to figure out how many grams are in a mole of each of these substances. So we know that 1 mole of N2H4 is going to be 2 nitrogens and 4 hydrogens. Nitrogen has a mass of about 14, so 14 times 2 is 28. We can kind of do this math. 14 times 2 plus the mass of 4 hydrogens, 4 times the mass of 1. So that gives us about 32 grams per mole. 32 grams per mole there. And then for N2O4, we know that 1 mole is going to equal the molar mass. Once again, 14 times 2. But this time we have 4 oxygen, so 16 times 4. And the molar mass adds up to about 92 grams per mole down here. Alright, so now that we have all that set up, let's go ahead and calculate. 400 times 1 divided by 1, so we don't need to type that part in, so divided by 32 times 4 divided by 2. So when I did that, I got 25 moles of H2O, and let me check my sig figs here. This was not just 400, but it was actually 400 with a decimal point. So I should make sure to do at least 3 sig figs in this intermediate answer. 25.0 moles of H2O. And then for my other reactant, we have 625 times 1.44 divided by 92, and then times 4. So I get 39.13, and I'll stop there because I'm actually only going to keep 3 sig figs in the end, moles of H2O. Okay, and so we are looking for the lower number because we know that once we run out of one of our reactants, we'll have to stop. So we can't actually produce 39.3. We can only produce 25 moles of H2O. And so let's label our limiting and excess reactants. And so our limiting reactant is the one that produces less. So limiting reactant would be N2H4. And then we are going to have an excess of N2O4. This will be available in excess. And so this is not our theoretical yield. Our theoretical yield is the 25.0 moles, but the problem is actually asking us to find the theoretical yield in liters of water vapor, not in moles. So I'm going to take my moles of H2O, and I'll just convert moles of H2O to liters of H2O. And I know that 1 mole of any gas, and I can use this because it says it's water vapor, 1 mole of any gas, it also has the gas sign in the chemical reaction, fills 22.4 liters. Okay, so there we have it. So we'll do 25 times 22.4. 25 times 22.4 gives me 560. And that it would be liters of H2O. And to show that this value has 3 sig figs, I do have to put a decimal after that 560. So it should be 560 point liters of H2O, or you could write it as 5.60 times 10 to the second milliliters of H2O if you prefer to write your answer in scientific notation. Either way is perfectly acceptable because they both have 3 significant figures. So I'll go ahead and box both those in. Either answer is acceptable. So this is our theoretical yield. Now, because it gives us a line to write our answers on, we definitely need to make sure we record our answers in the correct spot. So I'm going to come on up and I'm going to actually fill my answers in red so it's very clear. And I'm going to put 560 with a decimal point liters of H2O. And remember that your unit needs to include the substance as well as the actual unit. Alright, so there is our theoretical yield. Now that we want to know how much excess is left over. So we need to figure out how much of our N2O4 was consumed when we made 25 moles of H2O. So I'm going to take this 25 moles of H2O and I'm going to start with that. H2O. It's actually 25.0. I'm not doing a very good job of keeping track of my sig figs here. 25.0. Alright, so we'll go from moles of H2O to moles of our excess reactant, N2O4. Then we can go from moles of N2O4 to grams of N2O4. And then, since our original amount was given in milliliters, we'll have to go from grams of N2O4 to milliliters of N2O4. Alright, so for our mole to mole ratio, we just look at our balanced chemical equation. So N2O4 has a coefficient of 1 and H2O has a coefficient of 4, so that would be a 1 to 4 ratio. For our gram to mole conversion, we know that 1 mole of N2O4, we already calculated it out to be 92 grams. And then for our gram to milliliter conversion, we're using our density value, but notice that we have to flip our conversion factor from how we used it before, because this time grams are on bottom and milliliters are on top. So our 1.44 goes on the bottom, 1.44 grams per 1 milliliter, or 1 milliliter per 1.44 grams in this case. So then, when we calculate this out, let's go ahead and do this. 25 divided by 4 times 92 divided by 1.44. So when I did all this, I got 399.306. But of course, we need to round just to 3 sig figs here. So let's go ahead and we'll keep these and look at that next digit over. So this is going to round to 399 milliliters of N2O4, and this is the amount that's used. So now we just need to figure out the excess, and we'll do that by subtracting the amount used from our original amount, the 625 milliliters that we started with. So 625 milliliters minus 399 milliliters. Notice that neither of these has decimal places, so our answer should be rounded to a whole number at the end. 625 minus 399 gives me 226 milliliters of excess N2O4. So we will box that answer in as well. That's our second answer, and we'll go and fill it in at the top. So how much excess is left over? There are 226 milliliters of N2O4. That's the amount of excess. And then last but not least, it says if the reaction yields 345 liters of water vapor, what is the percent yield? And so right in the problem, it's giving us our actual yield. So I'm going to label that. This is our actual yield right here, and we already calculated the theoretical yield. We even labeled it. It's right here. So we have our theoretical yield. Our actual yield is given, so to calculate our percent yield, we are just going to do, so our percent yield will be equal to the actual divided by the theoretical, and then times 100 to convert it to a percent. Okay, so let's do that. So our actual 345 liters of H2O divided by the 560 liters of H2O that we expected. So when I do that, 345 divided by 560, I got 0.616, which is equivalent to 61.6%. And since we have three sig figs here, we'll leave it as 61.6, but more often than not, you will actually see percent yields rounded to a whole number. But in this case, I'll go ahead and leave it as 61.6%, since both of our values had three significant figures. And that is everything. We've filled in all our blanks. We've solved all parts of the problem. This is the kind of problem that you can expect to see on a stoichiometry test. To be able to go all the way through this process of balancing the reaction or writing the reaction, calculating the theoretical yield and the amount of excess reactant, and lastly calculating the percent yield for a reaction.